Okay, Bismillahirrahmanirrahim. So today we are going to start with the fourth lecture of our course. And in this lecture, we are going to talk about the model response spectrum analysis. So if you remember, in the previous lecture, we discussed the multi-degree of freedom systems, the response history analysis, as well as the response spectrum analysis. So I decided to discuss more this procedure as it is used in the design as well as relevant to the multi-degree of freedom system. So the placing them at the fourth lecture was crucial. Let me take this pen. Okay, so let's talk about the free vibration in an undamped system. Okay, so let me just assume this single degree of freedom system. Okay, if it is an undamped system, so it will be only having a stiffness, and it will not have the dashboard to represent the damping in the system. So we just have only stiffness here. This is stiffness here. Okay, and a mass. And let's assume that this mass is acted by an acceleration. Okay, so if it is freely vibrating because of this acceleration, so what will happen is that the spring will extend. So there will be a stretch in the spring. And let's represent this by the amount of stretch is x. Okay. Now the classical equation of motion for an undamped freely vibrating single degree of freedom system or a system with no forcing function can be written as m x double derivative, so there is acceleration plus k x is equal to 0. So if there is no any forcing function, so this right side will be 0. And if there is no damping, so also the damping and the velocity term will be equal to 0. So we just have these two terms, mass time acceleration plus the stiffness time the displacement. We're all okay. I think there is no issue. Okay, there is no issue. So what you see in this equation, there are two terms. Mass experiencing an acceleration. So let me just write here. This is mass experiencing an acceleration. Now this is one force, and then there is a second force that is equal to the stiffness of the spring, stiffness of spring multiplied by the displacement of the spring. This is another type, the other force type in the SDF system, and these must be equal. It must be opposite in order to have equilibrium in the system. Okay, now since we are dealing with the multi-degree of freedom system, what we do is that the same equation is used also for the multi-degree of freedom systems, but instead of just a single quantity, the x and x double dash m and k, they are considered as vectors or matrix. So m, x, k, x are in vector form or vector and matrix form for a multi-degree of freedom system. So if you are analyzing multi-degree of freedom system, that same equation will be used, but the only difference is that mass will be in matrix, k will be in matrix, and x and x double dash, they will be in vector form. Okay, so instead of x representing a displacement, it will represent a shape vector. So what is important to note, we just mentioned here, that x vector, the displacement vector, will represent a shape vector. And it will represent a shape vector that is oscillating in a simple harmonic motion represented by a sine curve. And the oscillation is represented by sine curve. Okay, and the number of oscillation in a given period of time is the frequency of the system or the vibration. So how many oscillations it covers in a given time is basically representing the frequency of that multi-degree of freedom system with that particular shape vector. So therefore, the displacement in the previous equation can be written in terms of time as a shape vector multiplied by a sine function with a frequency of oscillation omega. Okay, so we just mention here. For example, this displacement vector will be represented by the x as a function of time, which will be equal to the shape vector times the sine omega t. This is the sine curve that represents the harmonic motion. Okay, this is the shape vector Okay. And x will be the displacement of each flow. The acceleration or the second derivative of the displacement can be written if we take the derivative of that same equation. So it will be equal to minus omega square, and again x shape vector into the sine omega t. So this is how we can write the acceleration of each flow. So if you substitute these two back into the main equation here, okay, if we put these values in this equation 1, and if we also, okay, so we write the equation number 1, yeah. Is it minus omega square m x, the shape vector, and sine omega t plus kx sine omega t is equal to 0. This is the equation we can get. Okay, now in this equation, if we divide both the sides on sine omega t, so let me just write here, if you divide this by sine omega t, so you are left with is k minus omega square m, and that is multiplied with the x vector square is equal to 0. So this is the main equation, and this equation represents a classical eigenvalue problem. So this is the classical eigenvalue problem. Okay, so now in this equation, we just write here. Oh, this is M, sorry. This one is mass. So in this equation, x is the eigenvector, which basically is representing the shape vector, and mostly we call it as a mode shape. And you have another term that is omega square. It is the eigenvalue. Okay, or it is basically the square of the frequency of vibration corresponding to a particular mode shape, which can be related to a period of vibration t. So for this equation, there are as many solutions to this problem as there are mass degrees of freedom in a lump mass system. So the number of solutions will depend on the lump masses. Okay. Okay. There is only one corresponding eigenvector for each eigenvalue solution. So for every solution, there will be one one eigenvector for each eigenvalue. Okay. So every solution will give you mode shape, and it will give you the frequency of vibration of that mode shape. And each mode shape is unique and has only one corresponding frequency or a period of the vibration. So let me just take an example. So if we have this three-story frame, okay, let's make it here. Okay, it has 3 stories, and let's say it has lump masses here, lump at the floor level. So this is the structure at rest position. Now let's assume that this frame is vibrating, oscillating in mode 1. Okay, so let's make this and let's also make this one, second one. So just make this as well. Okay. So in mode 1, what will happen is that in let me just show you the side sway of this frame. So the column will do like this. The same on this side, column will do like this. Okay. So if it is vibrating on the right side, if it is vibrating to the left, this is what the column will do, and this is what the columns will do. Okay, so this will go back and forth laterally under mode 1. And we can identify this mode by looking at the mode shape where all the floors are moving in the same direction. That will represent the mode 1. In mode 2, so let me just make it, it will be, the column will move something in this manner. So just make it, yeah. Okay. So you can see now that the top floor is moving towards the right direction, but the first and second floor they are moving in the left direction. So you can see that some masses are moving in one direction and the other masses are moving in the other direction. So this is representing a mode 2 that will have its mode shape like this and will have the oscillation period as T2. To understand this mode shape, you will see that if you look at the deflected shape of the structure and also the position at rest, so you will see that this kind of mode shape will make one knot, one point from where it will pass and will give an indication that there is only one knot in this vibration mode that will represent to the mode 2. If we look at the third mode of this structure, so we will see that let's say the first mode is moving, the top floor is moving in the, let's say, right direction. This is moving in the left direction. This is moving in the right direction, and then this. Okay. So again, it is moving in the right direction, in left direction, in right direction, and then else. Okay. So in this mode, you can see that this is now the mode shape for mode 3, having the oscillation time period is T3. Okay, and if you compare this with the original with the deflected shape, so you can see that there are two crossing points, these two knots that you can see there, and when there are two crossing points, this will indicate the third mode. And if you look at the higher, uh, the taller structure, so you can have even more modes than this. But these are the minimum three modes of an frame where the masses are allowed to only translate in the lateral direction. We can have other modes, the higher modes, the rotation modes, the vertical movement, and so on. But these are important for the description of the lateral movement of the structure. So, what is important for the model analysis of the structures? One of the key parameter is the participation factor and the participation function. So we have discussed this while we were talking about the multi-freedom system. Participation factor and participation function. So the participation factor, it is defined as a scalar or intended to measure the relative contribution of mode n to the total system state. So participation factor, it's represented by gamma n. So it's a scalar quantity intended to measure the relative contribution of mode n. Relative contribution of mode n to the total system state. So how much a given mode contribute to the total system response. Now, later on in the analysis, we will see that the participation factor itself is not has a very little meaning because it depends upon the arbitrary number used to define the mode shape. For example, if we look mathematically, you already talked about this in the previous lecture. Let me just write here again in a simple way. So participation factor is equal to the summation of floor masses with the mode shape divided by the again the floor masses divided by the mode shape with the square of each term. Okay, so this is how we can mathematically calculate the participation factor. Now, in this equation, if you see here, mass at each floor will be constant, but mode shape can vary. Okay, so whether you are using the original mode shape or you are using the normalized mode shape, the gamma factor will change. So gamma factor is dependent on the mode shape. Okay, but we will see that the participation function, it does not change, and for a given mode, it's a constant value. So let me just write here. is constant for a given mode. Now, it is important to note that regardless of the arbitrary original number used to describe the mode shape, the participation function will always result in the same vector because the participation factor will change based upon the number used to describe the shape. So you will see that the participation factor will be a number and participation function will be a vector. So this will be constant while this can vary. Now, while we will analyze each mode in a multi-degree of freedom system as a single degree of freedom system, so as we mentioned even last time that a multi-degree of freedom system will be split into a number of single degree of freedom systems. Okay, and it is the participation function, this vector, that will provide the conversion that determine the response of each mass in the mode. Okay, so let me just write here. Participation function provide the conversion from SDOF to FDOF for each mode. And the response of each mass, so means every flow in a mode. Okay, so when you use participation function, it will convert a single degree of freedom system response to multi degree of freedom response. Okay, so you'll be able to understand how each floor is responding with time. Now, the participation function, we already talked about this. Mathematically, it can be obtained. We just need to multiply the gamma factor for a given mode with the mode shape of that mode. So it will give us the participation function. Now, there is some interesting fact regarding the modal combinations, and it's quite useful as well. The participation function vector is when you added them together for every mode, the resulting vector is a unit vector. Okay, so for example, if you sum all the modal, let me just write n is equal to 1, all the modal participation function, their resultant is a unit vector. Okay, so in this case is the number of modes in the number of level as well. So if you sum participation functions for every mode, which are basically vectors, the resulting vector will be just a unit vector. And this will describe as the accuracy of our analysis, because at this stage you can check if you get 111 for every floor. When you combine the participation function, it means that your calculations are correct till this point. And 1 means that there is a 100% contribution when you sum the total modal combination. The next key parameter in model analysis is the model mass participation. So each mode will have a corresponding effective mass associated with it, which is a percentage of the total mass of the structure. The sum of all model effective masses equals the total mass of the structure. To calculate the effective mass participating in a given mode, we can write them as M effective in a given mode. That will be equal to sum Mi phi n n. Okay, so floor mass is the mode shape, and then this denominator square, okay, divided by again the I is equal to 1 to n, the summation m mi and phi n square. So it is just like the participation factor, but the only difference is that the denominator is square instead of just the mi phi. Now, even as I mentioned last time that the seismic codes it stated that the analysis shall include a sufficient number of modes to obtain a combined modal mass participation of at least 90%. Okay, so you take sufficient number of modes when the contribution of mass becomes 90%. It's 90%. Now remember that it doesn't mean that the 10% weight of the building can be ignored. So it's only the code way of limiting the number of modes in the analysis to only significant modes. Okay? If a mode has a very small mass associated with it, then its participation in the response to the earthquake is assumed to be negligible. So sometimes, or in majority of the cases, the first two modes or the first three modes are always sufficient to contribute to up to 90% of the total mass. Now, how we determine the forces and the story shear? So each mode and its corresponding period of vibration will be analyzed individually as a single degree of freedom system using a response spectrum. So what we do is that every mode is assumed as SDOF. So each mode is treated as SDOF and also using the response spectrum. So you need the SDOF properties and you need the response spectrum in order to calculate in order to analyze a given mode of a multi-gravity freedom system. The forces will be applied to the mass in each mode based upon the equation we write here. So in a given mode, the floor forces can be obtained as Fin is equal to A in O Mi gamma in phi n. Okay, where if I is the floor forces, okay, and this term A in naught is the spectral acceleration, and this is obtained from the response spectrum So it is obtained from the response spectrum at the vibration period of that mode. So if it is for a single earthquake, you just need response spectrum. But if it is for the code design, then you need to use design spectrum instead of the response spectrum. So remember that the spectrum given in code is a design spectrum. Mi, we already know representing mass at each floor. And this term here is a participation function. Okay, so once you get the participation function vector, you multiply that with each floor, you multiply that with the spectral acceleration at mode 1, you will get the floor forces. Okay, and once you know the floor forces, you can calculate the story shear easily. Okay, for example, let me just mention here, say if we have floor forces in this way for a 3-story, this is F1, this is F2, and this is F3. We can write in a reverse way. So the story shear here, let me just draw the shear diagram. It will be like, in this story, it will be all equal to F1. But as you move to the second floor, it becomes F1 plus F2. So this is F1 plus F2. And if you go to the last floor, it becomes F1 plus F2 plus F3. So once you have the floor forces, then you can just keep summing as you move up the building. So you can calculate the story shear at every story level. Okay, so regarding the response spectrum, because this is something that we need in the design or in the response analysis. So response spectrum is basically a graph generated for a specific site by a geotechnical engineer that plot the maximum acceleration experienced by a single degree of freedom system mass for a spectrum of periods of vibration based upon their site-specific characteristics. So response spectrum basically, and we already know, is the maximum acceleration, is representing maximum acceleration experienced by its DOF system. Okay. So remember that when a site-specific response spectrum is not available, then the seismic code provide a method for generating a design response spectrum for modal response spectrum analysis. Okay, so if you do not have a response spectrum at a site, so you can use the code procedure to generate design spectrum. So how the spectrum look like? If this is the y-axis and this is the x-axis, so an x-axis of this spectrum is the value of vibration period, t in seconds, and y-axis there is spectral acceleration. And we can say spectral response acceleration, SAG. And the easiest way of plotting this is that it starts from some value here and it linearly increase to certain value, it remain constant, and then it uh, reduces with uh, some function. So where it starts, if we look at the current code in the building code of Pakistan, there are terms CACV. And in terms of the IBC, let me just mention that for the IBC. So IBC gives here that the spectral design spectral acceleration, which is the plateau value, is equal to SDS, while this value at the T0 is equal to 0.4 SDS. So it's just like a kind of a PGA, and there is a spectral acceleration called as the short period spectral acceleration. And this branch of the design spectrum is described by an equation that is equal to SD1 divided by T. So it is in the same way you can use CV divided by T, and this is a CA, and the same way you can use the PGA value as well. And then there are the corner of this plateau. So this period here, this corner period is TS, and this period is T naught. Now TS is equal to SD1 divided by SDS, while T naught is equal to 0.2 TS. Calculation is required in order to have those time period. Okay. And this branch in the new code in the IBC continues till a time period represented by TL. Okay, and that varies from region to region because of the various variation in the seismicity of the area. But this is the typical shape of the design spectrum given in the code. So once the forces and story shears are calculated for each significant mode, the story shear must be combined using some rational method. So this is something important to notice, that when story shears are obtained, they should be combined using the SRSS rule or the CQC rule. So we already talked about the SRSS combination and the CQC model combination. So you can use either of these two if the vibration period are apart from each other. So SRSS is a good approximation, but CQC is more accurate. So what you have to do once story shear are obtained for every mode, then you have to combine them by SRSS or CQC So you get the total story share. Okay, and from those total story share, you have to go back and calculate flow forces. Okay, so you have to obtain the corresponding floor forces. So it's just like your story share, and then you have to do back calculation in order to obtain the corresponding floor forces for final story share. And once you obtain these floor forces, then you can use them in the analysis of the structure. There is one other thing that we have to note, that the force is calculated from the design response spectrum shall be divided by a quantity R over IE. Okay, so R over IE uh, in order to produce the design level forces. Okay, so if we have A in naught, then A in naught has to be divided by the R over I E. Okay, to obtain the design level forces in the structure. Okay, once you do the dynamic model analysis, you have to also pay attention to the scaling of the dynamic base shear. Why? Because whenever you do the model analysis, which is a dynamic procedure, so the base shear is always less than the base shear obtained from the ELF. So let me just mention that the dynamic base shear is always less than the base shear obtained from the static. So for dynamic, we use the response spectrum analysis, model response spectrum analysis, and for static, we use the ELF, the equivalent lateral force procedure, the equations given in the code. So what we basically do, our the requirement for the code is that the V dynamic should be at least equal to the 0.85 times VELF. So if we have a dynamic force that is less than this, so then this will be the governing one. Or maybe I can write here minimum. So the minimum dynamic force will be equal to 0.85 V ELF. So you obtain the base shear using dynamic procedure, then use the static procedure, obtain the base shear, take the 85% of the static base shear, and if this is greater than the dynamic one, so then this becomes the value, or if it is the dynamic is more than this and less than the V static, then you can assume that. But anyway, this is what the code says, that you can take up to 0.85 times the static base shear. So once you reduce the base shear, then you have to multiply each story shear and each floor force with that scaling factor. Okay, so we will use the scaling factor in order to finally correct the story shears. Okay, so now let me just give you an example of a problem, how we use this procedure in order to solve an actual problem. Okay, so there is a frame. Okay, there's a 5-story frame. Okay, and let me just write here the height of each story. So the first story is having a height of 16 feet, while the other 4 stories they have a height of 13 feet. The masses are written in terms of the weights, which is 2505 kips, okay, and then 3132, 3132, 3132, and 3132 kips. So mass sometimes it is written in the kips or in the pound or in ton. So for this frame, the building data is given. Okay, the response modification factor is 8, which you know is the factor that we use to reduce the elastic forces. The risk category of this structure is risk category 2, which is the normal occupancy structure. The structure is regular, both in plane and vertically. Okay. The site location of this structure is given because if you are designing this as per the IBC, so it's important to know where this structure is located. The total weight of the structure is equal to 15033. So if you sum the floor masses, you will get 15033 kip. And the model period for mode 1 obtained from the computer program is 1.45 seconds. Now the ground motion data. So the site class is D, which is a stiff soil. The regional values for the spectral acceleration are given. The SS is 1.124 G, and the S1 is equal to 0.42 G. Then the value of the soil amplification factor FA is given 1.05 and FV is given, which is 1.57. So using the IBC procedure, we can convert SS to SDS, okay, which is equal to FA into SS. And then also you have to multiply this with 2/3. The same way you can convert S1 into SD1. So this is FV into S1 divided by the, multiplied with the 2/3. Okay, so in case of the IBC, the value for the design are 2/3 of the values given in the code SS and S1. Now, this problem is obtained from another example where the base shear VB obtained was 737 kip. So this is a problem that was already analyzed using the static procedure, the equivalent lateral force procedure, so ELF, and the base shear for that is 737. Now we are using the modal analysis to compute the base shear, story shear, and the floor forces for analysis. In order to understand how the dynamic modal analysis procedure is used for the analysis of structure. Okay, what I will do is that I will take a break. It's almost 16:15, so we'll meet at around 16:30 to continue the remaining lecture. So we'll continue from 16:30 to analyze this problem.